you have a new visitor here, Baldomero Coll-Perales. You go by Baldo, I understand.
Yeah.
He got his PhD in 2015, if I remember correctly, in the University Miguel Hernandez, which is in Spain. Not too far from Madrid, I understand.
Driving, it's 4 hours driving.
Okay, maybe a little farther from Madrid than I thought. 4 hours. Okay. And he'll be spending the next year here, and he's looking for research projects to get engaged on. So let's hear what you've been working on.
Okay. Well, thank you for the introduction. Well, let me take this time also to thank Marco and Professor Ray for supporting my application a year ago, and that's the reason why I'm here today, so thank you again. Well, I'm going to summarize in this presentation the work that I've been doing in the field of device-centric technologies. First, I want to show you where we are in Spain. This is the Alicante area, this is Madrid, Marco was saying. So I'm with the UWICORE Research Laboratory, that is part of the Communication Engineering Department at the Miguel Hernandez University of Elche. Our group is led by Professor Javier Gonzalez. We are a small group, an active one, I should say, with 10 to 15 members, depending on funding, project, and so on. And these are our research expertise and current research fields that include vehicular communication and network for the connected and autonomous vehicle, wireless communication for industrial environments for the factory of the future and the industry 4.0, and heterogeneous device-centric wireless network, that is where my work is included. As I told you, this presentation is intended to summarize my previous research activities in the field of device-centric technologies. And to begin with, I will introduce you this concept. First, just a figure to see the opportunity of this technology. The thing is that users spend on average around 3 hours per day on their mobile phone. This is actually a high value and something that could draw your attention if you are concerned about your production, or if as a parent you are concerned about the time your kids spend on social media and digital media or gadgets. If you are a wireless engineer interested in making wireless ubiquitous, you may think that actually a mobile phone is a device, a powerful device, that is left doing nothing for more than 20 hours a day. Fortunately, there is a trend towards making devices to take a more active role in wireless communication and networking. Device-centric wireless communication represents an emerging alternative to cell-centric solution. In cell-centric networks, the mobile station directly communicates with the base station through a single hop cellular link, and the link budget reduces with the distance. The device-centric wireless network exploits the communication and computing capabilities of mobile devices to implement device-to-device communication. In device-centric wireless network, smart mobile devices can provide wireless connectivity to other devices and hence act as a bridge with the cellular infrastructure. The integration of device-to-device communication and cellular communication is referred as to multi-hop cellular networks. Multi-hop cellular networks are capable of providing more homogeneous quality of service levels by means of substituting long-distance and generally non-line of sight cellular links by multiple shorter links with improved link budgets. The device-centric wireless network can also exploit the mobility and the storing capacity of mobile devices to implement opportunistic networking schemes. Opportunistic schemes establish communication links when good communication conditions are found. This operation may result in possible end-to-end transmission delay, and then opportunistic schemes will concentrate on delay-tolerant services. The device-centric wireless network is also present in the standardization domains. In particular, Release 12 of 3GPP introduces what is called proximity services, which devices can autonomously discover nearby devices. When devices discover each other, they leverage the cellular infrastructure in order to maintain, establish, and control this communication. The possibility to do device-to-device communication was introduced in Release 13 under the term direct communication, which actually can utilize not only cellular LTE technologies, but also Wi-Fi ones. The concept of multi-hop cellular networks was also introduced in Release 13 under the term user equipment to network relay, In this case, a mobile device can act as a relay and provide wireless connectivity to what is called remote user equipment. In Release 13, these technologies are limited to public safety use cases. So this concept of multi-hop cellular network is extended to non-public safety use cases under Release 14, since there is a lot of interest to use LTE technologies to connect and manage machine-type communication devices, such as wearables, that have the benefit of almost always being in close proximity to a smartphone that can act as a relay. Something that we find really exciting is the recent attention that industries are starting to pay on device-centric wireless networking solution. This is the case, for example, of 4G that was presented by Vodafone at the last Mobile World Congress. 4G is an application that increases the speed of data transmission of 2G and 3G devices by connecting these devices using Wi-Fi technologies to 4G devices that work as a relay or hotspot with the base station. For us, this is very exciting since this is the first time that a cellular operator releases some mobile devices to act partially as a network node in order to improve the quality of service of all the devices. Continuing with the agenda, an important part of my previous research activities focused on validating and quantify the benefits that multi-hop cellular network can provide over a traditional single-hop cellular system using experimental field tests. And to this end, we developed the MHOP testbed. This figure illustrates the MHOP testbed and shows how the destination mobile node can be reached through a single-hop cellular connection or a multi-hop cellular connection in order to allow for the performance comparison. The multi-hop cellular connection can access to the cellular infrastructure using an hybrid mobile node that forwards the cellular data towards the destination mobile node in real time without downgrading the overall network performance using D2D communication and these intermediate mobile relays. The nodes that integrate the MHOP platform have the capability to continuously geolocate their performance since they incorporate GPS receivers. The use of the GPS also allows to time synchronizing all the MHOP devices. The MHOP platform incorporates 3 different types of devices with different connectivity capabilities. The hybrid node and the destination node with cellular and D2D connectivity, and the intermediate mobile relays with D2D connectivity. The cellular connectivity is included in the MHOP platform using a Nokia 7720C handset that supports HSPA technologies. It also incorporates the Nemo Handy application, which is a powerful radio monitoring tool that allows to monitor in real time the operation of cellular networks and that provide very important KPI parameters. The mobile nodes consist of conventional laptops transmitting over EU211. As I told you, this is a 3GP candidate for D2D communication. This node monitors the transmitted and received packets using both the built-in wireless interface and a virtual interface created using an ADEC wireless express card. We also developed a GPS and a packet sniffer software in order to time and georeference all the logged radio measurements. Using the MHOP testbed, we reported what is, to the best of our knowledge, the first experimental field test that validate and quantify the benefits of multi-hop cellular networks and the condition under which such benefit can be obtained. We conducted this test over the commercial live cellular networks of Orange in the city of Elche. For this test, the cellular links are operating in HSPA at 2.1 GHz, and the D2D links over EU211G at 2.4 GHz. Most of the tests consist on downlink transmission of large files from a server located in our lab. We conducted field tests under diverse scenarios, and the performance benefits of multi-hop cellular network was demonstrated for this set of use cases. I've selected 3 of these use cases for this presentation, but you can find the details for all the other use cases in this publication. Well, the first use case is aimed at demonstrating the capacity of multi-hop cellular network to provide high quality of service level at large distances to the serving base station. The tests were conducted in this urban scenario and the different configuration for the multi-hop cellular communication. This configuration will be referred as two hops, since we have a D2D link and a cellular link, with a separation distance between the node of 60 meters. Other configuration include 3 hops with a separation distance between node of 90 meters, and 4 hops and a separation distance between nodes of 120 meters. It is important to note that the location of the destination node in this test is fixed, while the location of the intermediate node and the hybrid node varies with the multi-hop cellular configuration. So the higher the number of hops, the closer is the hybrid node to the serving base station. Here in this test, the nodes are static, they are not moving. They are experiencing line of sight condition, but the selected scenario is a busy street with pedestrians continuously crossing over the links. This figure shows first the throughput as a function of the distance to the cellular base station of the experience by a single hop cellular link. What we can see in the figure is that throughput of the single hop cellular link decreases with the increasing distances as a result of the higher signal losses and the lower link quality. For this test, we use the Nemo Handy application in order to lock the terminal to a particular base station and to avoid the execution of handover. So here, maybe a handover could be executed, but we are locked to the base station in order to have a more stable scenario. Using these results as a reference, the figures show now the throughput at the destination node of a multi-hop cellular configuration composed of 4 hops and 120-meter distance between the nodes. So we can see here that a destination node located 780 meters away to the base station experienced almost 4.2 megabits per second. If I move the throughput of the destination node to the location where the hybrid node was located, what we can see is that the throughput of the destination node is upper bounded by the cellular throughput experienced by this hybrid node. If I include now the throughput at the destination node for all the other configuration, we can confirm that the throughput of the destination node is upper bounded by the cellular throughput that the hybrid node was actually experiencing. So this test demonstrates that multi-hop cellular communication can provide users located at large distances to the base station with quality of service level close to those experienced by a node that are at shorter distances to the base station. This second use case is aimed at demonstrating the capacity of multi-hop cellular network to increase indoor quality of service levels. The tests were conducted in this shopping center in Elche on a Friday afternoon when the shopping center was crowded. In this test, the serving base station was located 500-meter distance to the entrance. Here is the entrance of the shopping center. And we tested also different configuration with 2 hops, 3 hops, and 4 hops. Here the figure illustrates the configuration for 4 hops communication. And there is always a separation between the mobile relays of 75 meters. At the start of the test, the hybrid node is located outside the shopping center, and the other nodes are located inside. So when the test starts, all the nodes move 75 meters inwards, with the hybrid node ending just inside the shopping center. Here the figure shows first the throughput of the single hop cellular link as a function to the distance to the entrance. So here, 0 represents the entrance of the shopping center, negative distances are outdoor location, and positive distances are indoor location. What we can see is that the single hop cellular link can only provide outdoor quality of service level close to the entrance. On the other hand, multi-hop cellular connection with 2 hops can extend the outdoor quality of service level 75 meters inwards. If I increase the number of hops, we can see that higher quality of service level can be provided at inner distances in the shopping center. Actually, the 4 hops configuration in red can extend the outdoor quality of service level 225 meters inwards. So this test demonstrates that multi-hop cellular communication can increase indoor quality of service levels. The figure also shows the possibility that multi-hop cellular network provide to extend the cellular radio coverage. Since here we can see that the single hop cellular link finishes at these distances, but with multi-hop cellular communication, we can extend the cellular radio range a couple of meters for this configuration. Here again, we are using the Nemo Handy application to lock the terminal to the outdoor cellular base station. So here probably there is another indoor base station that the mobile station will be having connected. But we are avoiding this using the Nemo Handy application, just to see what could be a next scenario where there is a coverage hole. And this use case is aimed at demonstrating the energy consumption benefits of multi-hop cellular communication. Here we are focused on uplink communication, since downlink communication will have required access to the serving base station to measure the energy consumption, which was not possible. Here we are comparing the energy consumption of a single hop cellular communication from a mobile station located inside a building with that of a two-hop connection where the destination node, that is actually source node since we are focused on uplink communication, gain access to the cellular infrastructure using an hybrid node that is located outside with line of sight condition to the source node and with the serving base station. The reported results show that the cellular transmission of the single hop cellular communication from the mobile station to the base station require on average a transmission power of 15 dBm. Here the figure shows the evolution of the energy consumption with time for the single hop cellular communication. Actually, we are showing the energy consumption per transmitted bit. On the other hand, the cellular transmission of the multi-hop cellular connection from the hybrid node to the base station require on average a transmission power of minus 20 dBm. The figure also includes now the total energy consumption of the multi-hop cellular connection that includes the energy consumption of the D2D link and the cellular link, which actually represent a 50% reduction in the energy consumption. So this test demonstrates the energy consumption benefit of multi-hop cellular communication. We also exploited the field test measurement in order to derive models useful to the...
Ask you about the previous plot.
Sure.
Where you said it includes the device-to-device link.
Mm-hmm.
Does it include both devices?
Yeah, both devices.
So when you're comparing a single hop link, you only have one device active.
Mm-hmm. Yeah.
Now if there's a multi-hop link, there's a second device that needs to be awake.
Yeah.
And that needs to transmit.
Mm-hmm.
And all that is included in that WINLAB.
Exactly. Yeah, for this test, we were not actually using a laptop as a source node. We were using another mobile devices, and both the source node and the hybrid node were equipped with the Nokia Energy Profiler that allowed us to figure out what's the energy consumption in the transmission for the D2D and for the cellular link.
Is it transmission energy consumption only, or total device energy consumption?
As much as we could, separate the energy consumption for all the processes that are within the devices. This is only for the energy transmission. What is required for the transmission. Since we are able.
There's another baseline energy consumption if the secondary, the forwarding device,
Mm-hmm.
normally would have been inactive asleep. And now it needs to be woken up in order to conduct the transmission.
Yeah.
There's another baseline energy consumption.
That we are not considering this.
Could be quite high, right? Any idea how high that is?
What we show is that the higher aggregate energy was related with the transmission. So there are other processes that are in the background that are consuming energy, such as the Bluetooth that could be active, the screen as well. But we experienced that the energy increases a lot when we started to transmit the information. So it seems that this is much more relevant than any other process that could be in the background. Well, we also exploited this field test measurement in order to derive some models In particular, we derive models, communication models of the communication performance of multi-hop cellular network that take into account the number of hops in the communication, the distance between the nodes, the visibility conditions, so if they are in line of sight condition or non-line of sight condition, and the communication setting. So in this example, it is we are showing the throughput at the destination node of a multi-hop cellular connection with two hops as a function of the distance between the ivory node and the destination node, and the line of sight condition between the ivory node and the destination node, and for no line of sight condition between the ivory node and the destination node. The figure shows that the throughput at the destination node is first upper bounded by the cellular throughput experienced by the ivory node. So as the distance between the ivory node and the destination node increases, the throughput starts decreasing. So from this distance onwards, the throughput at the destination node is upper bounded by the D2D link. We can see actually similar trends on the line of sight condition and non-line of sight condition. The main difference obviously lies in the distance at which the throughput starts decreasing, which is shorter, and the non-line of sight condition because of the worse propagation condition. This performance has what is called a symmetric shape, and we model it using a sigmoid function. We also use it some curve fitting techniques in order to derive the fitting parameters that best fit the modeling function to the empirical data, both for line of sight condition and for non-line of sight condition. We extended this measurement to a higher number of hops for the multi-hop cellular configuration. This is a figure for 3 hops communication with different visibility possibilities. We derive a general form to model the communication performance with up to 5 hops. I will not go into detail in this part, but all the details are here in this publication. Finally, I will summarize in this part the work that we have been doing to integrate opportunistic networking mechanisms into multi-hop cellular networks for delay-tolerant services. Delay-tolerant services include mobile video, file sharing, messaging or texting application, emails. So it is important to know that delay-tolerant services will represent a large portion of the mobile data traffic in the years to come. For example, according to Cisco estimates, mobile video will represent 72% of the mobile data traffic by 2019. Here, this is a real example of the buffering policy implemented on YouTube. Here, the buffer data is equivalent to 50 seconds. So we could delay or postpone the transmission of the remaining information as long as the playback time doesn't pass the buffer data. So we investigated how to exploit this delay tolerance in order to further increase the benefits of multi-hop cellular network through the integration of opportunistic networking schemes. We focused on a 2-hop scenario in which a static source node wants to communicate with the base station using a mobile relay with store, carry, and forward capabilities. This opportunistic multi-hop cellular communication takes into account the time needed for the D2D communication, the time the mobile relay stores and carries the information, and the time needed for the transmission of the mobile relay to the base station. Actually, estimating the time needed for each of these processes is equivalent to identifying the optimum mobile relay location at which the D2D transmission should start, and the optimum mobile relay location at which the cellular transmission should start. In order to identify these two optimum locations, we proposed this mathematical framework that in the objective function seeks minimizing the total energy consumption, which is the sum of the energy consumed by the D2D transmission, the store and carry process, and the cellular transmission. This objective function is defined subject to a set of constraints that ensure that the message is transmitted in the D2D links and in the cellular link, and that the base station receives the information before the service-dependent deadline. However, you may think that this optimum configuration can be unfeasible, since in practical setting it can happen that a mobile relay cannot be found at the identified optimal location. So in order to address this scenario, we proposed a set of context-aware opportunistic forwarding schemes that relax the need of a mobile relay to be located at the optimal location and time instant. These two proposals are named time-dependent opportunistic forwarding, or delay in short, and space-dependent opportunistic forwarding, or area in short. I will focus in this presentation in the second proposal, the area 1. This area proposal increases the search area around the optimal location where to search for a mobile relay. So if a mobile relay is found, then the D2D transmission is conducted. Then the mobile relay stores and carries the information and uploads it to the base station, probably from a suboptimal location given the variation in the selection of the mobile relay. This area proposal uses context information in order to estimate the radius of the mobile relay search area that guarantees with certain probability the presence of at least one mobile relay within this area. The context information that we are using is information that is present in cellular network, such as the spatial density and the spatial distribution of nodes within the cell. This figure shows the energy efficiency as a function of the distance of the source node to the base station. The reported results shows that the integration of opportunistic networking and multi-hop cellular network result in important energy efficiency gains compared to single-hop cellular communication for distances higher than 150 meters. This distance is because we need a gap between when the single-hop cellular communication doesn't work so well in order to reduce the energy consumption that this communication is using in the cellular link. The scheme that is actually achieving the major gains is the optimum but not always feasible configuration, but the area proposal achieves a pretty close performance than the optimum configuration. In particular, when the source node is located 300 meters away to the base station, the area proposal can reduce the energy consumption by 70%. This reduction level increases to 90% when the source node is at distances higher than 500 meters.
Excuse me, did you would you please explain why you consider energy consumption as a criteria and not the end-to-end delay for uploading the whole content? And in scenarios that you had the optimum, you had the solution with optimum energy consumption, what was on average, or what was the delay imposed? Did it actually result in a very huge delay, or?
Well, here what we are considering is that our service is tolerating us to delay the transmission, the end-to-end transmission, for 60 seconds. So we are actually exploiting this tolerance to reduce the energy consumption in our transmission. So here probably a single hop cellular communication will require also I don't know, 20, 30 seconds for the transmission. So we are using more time for the communication, but we are considering that our application allows us to delay the transmission.
Maximum,
yeah, this is our maximum.
If you consider the minimum delay, what was the energy consumption on that? If you try to minimize based on the delay, then how was the situation with the energy consumption?
Well, I don't have results for that here, but sometimes, using multi-hop cellular communication, you can shorten the delay in the communication. I don't have yet these results, but I could show you some measurement that we also did with
that's great.
Our test bed.
Okay. Can I ask a question?
Mm-hmm.
So the performance of your context-aware scheme depends on the prediction accuracy and mobility of the delay node, I think.
Mm-hmm.
So I'd like to know the assumption of your evaluation.
Yeah, here we are assuming that we are in a straight street, so all the nodes are moving towards the base station or in the other direction. So I have said the context information that we are considering is the spatial density of nodes within the cell. So with this spatial density, we could differentiate those nodes are moving towards the base station and the nodes are moving away from the base station. So again, we could, consider what's the density of nodes that are of interest for us, that are those that are moving towards the base station. There are other studies that consider that the mobile relay is actually a car. So it's much more easier to predict the direction of the cars towards the base station. But this is, a different approach. Yeah, okay. And here we have been focused on reducing the energy consumption, but we think that opportunistic multi-hop cellular communication can also help improve the network capacity by reducing the time that the cellular resources are utilized. So we focus on a two-hop uplink multi-hop cellular communication again, and we model this using space-time graphs. A space-time graph create dynamic sequences of graphs that represent the evolution of the node's location and connectivity with time. For this example, a node S has a message to transmit and has t seconds to do so. So at time instant 1, S identifies as potential mobile relays the devices 1, 2, and 3. At time instant 2, the space-time graph models the possibility these devices to establish a cellular link. It is important to know that the cellular transmission doesn't need to start immediately because here what we want is to exploit this delay tolerance so that these mobile relays could store the message and then upload them to the base station. So the space-time graph actually maintains the cellular links along the time. So the space-time graphs, actually what it's doing is to represent all the possible D2D and cellular links in order to identify what are the ones that minimize the cellular transmission time. Here in this study, we are focused on identifying what's the performance bound, the maximum capacity that we could achieve, and we are assuming a perfect knowledge of the node's movement and node's location. Here we are not considering a straight street like in our previous studies, but we assume that we know the trajectories of the devices within the cell. In order to identify this time instant, we also propose a mathematical framework that in the objective function seeks minimizing the total cellular transmission time from a relay to the base station. This objective function is also subject to some constraint. The first constraint guarantees that the D2D link between the source and the mobile relay is active for at least t D2D seconds. We find these t2D seconds using our empirical data and limiting the D2D communication range to a specific range. The second constraint guarantees that the message is completely transmitted also in the cellular link. And the third constraint guarantees that the cellular link doesn't transmit more information than what is received through the D2D link. So we also execute this mathematical framework for all the relays that are in contact with us. And the result is the identification of the relay and the time instant at which the D2D and the cellular transmission should take place. That, as I have said to you, they don't need to be consecutive in time. This figure shows the capacity gain of multi-hop cellular communication compared to traditional single-hop cellular communication. The capacity gain represents how many more opportunistic multi-hop cellular communication than single-hop cellular communication can be supported in order to achieve the same channel occupancy. So the results show that the capacity gain increases with the cell radius and with the service-dependent deadline. The minimum capacity gain is around 40%, and the capacity gain increases up to 270% when the cell radius is 770 meters and the deadline is set to 220 seconds. Now in this graph, it is included the performance of a scheme that use single-hop cellular communication, but in this link we are using opportunistic networking. So this is the opportunistic cellular scheme that's here in red. And we are also including the result for a multi-hop cellular communication that is not using opportunistic schemes in the D2D and in the cellular communication. This is the multi-hop cellular scheme. what we can see in this graph is that the benefit of opportunistic multi-hop cellular communication actually come from the combined use of both opportunistic networking and multi-hop cellular communication, since these two schemes cannot achieve by themselves these gains. Finally, based on this, what we consider promising result, we are extending these techniques. First, with the design of an opportunistic networking protocol that use efficiency-driven connectivity graphs that evolve in time based on the content and content condition. We are also evolving our MHOP testbed in order to integrate opportunistic networking schemes in the D2D links and in the cellular links. These two work are almost completed, so I would be more than happy to show you the results in some days. For example, what we were saying about this delay in the multi-hop communication. And just to conclude, let me say what are the main contributions of this work. We have contributed first to the experimental validation of the potential and performance benefits that multi-hop cellular network can provide over traditional single-hop cellular communication. And we have designed and evaluated some context-aware opportunistic forwarding schemes that increase the feasibility of integrating opportunistic networking and multi-hop cellular networks, and that can contribute towards achieving the 5G objectives in terms of energy efficiency and capacity. Well, that's all from my side. Thank you very much for your attention. Please, of course, if you have a question.
So, do you consider any policies to choose the mobile network in terms of fairness? Like in your shopping center scenario, let's say somebody works there, and you always choose that guy to use his phone to relay data. It seems like he's using his phone like all the time.
Yeah.
Do you consider any policy to choose?
No. I mean, for our test, we have a limited number of nodes, so we always selected the same one. But it's true that you should take into account some policies in order to not overuse some relays that could be at optimal location in order to be used as a relay.
So that's not one of the aspects that you work on?
No. I haven't said that, but in the use case of energy consumption, what we show is that with the energy that the source node of the multi-hop cellular communication has saved, since it's using another relay, you are saving energy since you are not communicating with the base station. This source node could act around 3.5 times as a relay for other devices. So this is like a moon game. So if we all contribute towards the multi-hop cellular communication, we are all gaining a benefit, so we can act as a relay other times. But a problem could be if we are overusing someone because this is a perfect relay, because it's in a perfect place.
And he's always there, like working in a shop, right?
Yeah.
I think right now you just consider the uplink. How about downlink? Do you consider downlink?
Yeah. In this work, we are also considering uplink. For us, I don't want to say this is much easier, but it is true that the location of the base station is fixed, so it is easier to recognize that you are moving towards this target. So in downing, the problem is that if you want to communicate with someone that's in the cell edge, you have to select the relay that is going to go towards this direction. And maybe you don't know the location of this mobile station. So the problem, although it could be reversed in terms of, mathematical framework, in practical setting could be more difficult to implement because you cannot know the location of this mobile station.
And another question is, when you model the relay choices, it's quite complex optimization problem. It can be solved online, or you need some heuristic algorithm to solve.
You mean this one?
Yeah.
It is true that we have to execute this mathematical framework for all the relays that have been in contact with us. So it could not be, scalable as long as the number of relays are increases. since here we are focused on identifying the upper bound, the performance bound of this communication, I mean, we are not worried about if this can be implemented in practical settings. So our objective is to design now a new scheme that doesn't need to take into account all the contacts with these relays, and that can create not these space-time graphs, but what we call connectivity-driven graphs, that you are not actually focused on a particular relay, but actually a region, so that you are characterizing a region, and in this region it could be that there are many relays, so you are limiting the name of iteration that you have to do in this optimization framework. I'm going to be here in year 1 year, so if you have further questions, please feel free to reach me in the office or whenever you want.
What do you think are the key questions that still need to be addressed for this to be practical and be part of some cellular system?
I mean, I think Vodafone with the 40 application is addressing a key question. We cannot connect all the devices to all the devices using Wi-Fi technologies, because we all know what the problem of Wi-Fi in terms of utilization, because the congestion problem. So sometimes it could be okay to connect, for example, 2G, 3G devices that are not experiencing such high speed, using I mean, the connection of 40 devices and connecting them to these 2G, 3 devices that could be as well machine type communication devices, such as your smartphone that's connected to your smartphone, I mean, sorry, your smartwatch that is connected to your smartphone in order to transmit something to the base station, or a sensor that is in a place and doesn't need to be connected to the cellular base station and could be connected to someone that is passing through this way and could be used to forward information to the base station. So I know it's not easy, I mean, a complete implementation of multi-hop cellular communication using all the devices as a relay. I mean, I think this is an ideal scenario, but there are some use cases where the implementation is easier and may have sense, because there are some devices with limited capabilities that could gain with the use of other intermediate mobile relays. Thinking about future possibility, I mean, what we are imagining is a world in which all the devices are sharing their resources. So if you are doing something with your computer and you need more resources, and you can forward me these processes, not only your communication, but also some tasks that you are doing. And we can communicate, and repeat with the answer of this process. But I mean, this is not for practical in close future, but yeah.
Has anybody looked at this as sort of a family setting? Or has anybody looked at this in terms of a family setting, or more generally household or company setting, where you have perhaps tens of devices that are paid under the same plan? Today you have multiple family members, and perhaps you have the iPads and your cars, so today there's probably some households that have 5 to 10 devices on the cellular plan. And a few years from now, maybe you have more than that, 10 to 20
sure.
on that plan. And if you take a company plan, where the company provides phones to people and many other devices, you could have thousands on the same plan. In that case, perhaps you have less of the fairness question. People are more willing to share resources.
Yeah.
Would it still make sense in that case?
But I know this is something to think about. Actually, 3GPP is also thinking on it, in the sense that the extension in release 14 is taking into account which is the provider of this traffic. I mean, in previous standard, if you are connected to a relay, the cellular base station only knows that this traffic comes from this relay. So you are bidding to this relay. And this is actually a problem since, I mean, you are not acting as a relay for someone, and in addition, you are going to pay for this traffic. So now 3GPP is extending and trying to provide end-to-end links, I mean, in order to know where the traffic is coming from, in order to differentiate different devices, although they are connected to the cellular infrastructure using the same relay.
Where the traffic is coming from, what do you mean by that? You're saying it differentiates based on where the traffic is coming from, right?
Yeah.
What do you mean by where the traffic is coming from?
I mean, for example, if we are connecting a sensor using a smartphone, you can differentiate that the traffic is coming from the sensor, not from this relay that is communicating with the base station. Also, this relay could actually aggregate the traffic from different sensors, and we could know what's the traffic, where the traffic comes from.
Okay. So if you imagine you have a very similar forwarding question with one or two phones, but it's a single household. One phone is downstairs, one phone is upstairs. So you're not halfway closer to the base station as in your scenario. Do you think it will still work? Will you still get a good game?
I mean, what we need to develop are some policies in order to identify what's your quality with the base station. Actually, in the evolution of the MO platform, we have developed an API that is able to read from the Qualcomm chipset and to get a quality metric from the chipset itself in order to know what are your conditions before transmitting the information. So we are performing opportunistic networking policies in the cellular phone using metrics such as the transport block size index, for example, that tells you what's your quality with the base station, your real quality. This is the information that the base station is forwarding to you. And also some other metrics such as the received signal SNR error. Also, you can take them from your chipset. So this is a good chance to decide whether to transmit or which relay to use as a forwarder of your information. Sure.
You good?
I think a better use case for this is car use as a relay. I know some startup already do that, use car as a relay. And I think the 3GPP recent release 14 already include the B2B communication. Sure. So they can use the B2B communication multi-hop to the base station. And we already have some other technologies. I think Suman already deployed some kind of bus to base station using one space. So a lot of the technology can be support that car user relay to connect with the base station, and we just need to communicate to the cars. So I guess we will have a lot of cars. We have a lot of choices to the relay. So in that case, fairness should not be a problem. Because you have more choices. In that case, you can randomly choose one, and next time you choose another one. And the car is much powerful, so we don't care about the energy. I guess for this kind of use case, D2D communication with car, involving car should be the best use case nowadays.
I haven't said that, but Vodafone has presented a 4G project, but they also have a project called Cloud Cell, where cars are used as a hotspot for user. So while the car is moving, the user inside the car are connected to the car, and the car is forwarding information. But when the car is stopped, user around the car can connect to the car, and then the car is the one that is forwarding information to the base station. So they are creating like small cells using cars.
The cars make a lot of sense in two ways. You're not energy constrained, and you can use larger antennas, better antennas than on a small handset. The disadvantage of cars is that usually you don't change them as often as your phone. So if you don't have some, you would need some sort of pluggable network module that you fixture out and put the 5G in, and then 2 years later you pull it out and put the 6G in, right? I mean, right now you have plenty of cars on the road that they have 3G, and there's no point whatsoever in using that.
It's more challenging to select a car while they are moving because of the propagation conditions are different. They are faster speed, they are moving at faster speed. But yeah, you are right that the capability of a car as a device are also higher than the one of smartphones.
Are we also considering the interference we are adding with multiple hops? I mean, if you are relaying the same data, like 6 hops, you are dividing the throughput by 6, roughly.
Yeah.
Then, if these relays are like short links, and we can reach out like to the, let's say, 5th node in the road, right? Directly from base station, then how do we optimize this?
We know that, I mean, communicating with D2D communication based on .11 can have these problems. We know that there are different channels that are not overlapping, so we can create different networks between D2D communication in order to have.
Yeah, let me correct myself. When I made this comment, I was thinking about car-to-car communication where we have just 10 megahertz channel for safety.
Okay.
Right. In that case, we don't have any other channels to use.
Yeah, I see.
So, if we want to use it in V2B, maybe we should consider the distance to the nodes between the relays and so much on. Because in that case, we don't have many channels to use.
Yeah.
I mean, the bottleneck is somewhere else. Is in the bandwidth, right? I'm just thinking out loud.
Yeah. But I think it's also that cars will not be already equipped with ECRC or .11 variants like .11p, but also LTE technologies are being developed for B2B communication as well. So we could balance the traffic among vehicles using intelligent mechanisms. I mean, one hop using LTE, other hop using ECRC, and so on.
It's usually useful to compare these technologies for the same spectrum use. If you, as an operator, you can look at that and say, well, unlicensed band, that's free for me, so of course I'm happy offloading some traffic there. And by doing this form of multi-hop as you implement it, I can more efficiently use the spectrum I paid for and then offload someone going in a longer range for onto Wi-Fi. But I can also just stick up a Wi-Fi access point at my base station and use both as in a single hop mode. I can, in parallel, I can use my paid spectrum and the unlicensed band Wi-Fi spectrum serving single hop. So that would be the interesting comparison, and then showing that the multi-hop approach still outperforms the single hop approach. Which it probably do in many cases.
Yeah, sure. I mean, we are actually offloading many traffic when we are in scenarios like this. We are not connected probably to by station, but to the access point.
Right.
Any idea about the restriction for using others' phone to relay? I mean, do we need the permission, like user permission?
There are some studies considering what's the benefit of being used as a relay. I mean, if you are a user willing to contribute, I mean, to the community, let's say, you are happy to collaborate because when you need this communication, you will be also, I mean, you will also find another relay that will help you. The thing is that, but for example, a college of mine in Spain studied the problem of selfish node. So someone will tell you that I'm going to collaborate with you as a relay, but then I'm not forwarding the information. So I'm only doing tasks for, I mean, gaining some virtual coins that I'm being used as a relay. We can't control this selfish node since the base station can, I mean, it's like an eye that can see everything what is happening within the base station. So we develop some policies in order to control these selfish node that are not collaborating, in fact, in intercommunication. There are some also policies that are called watchdog. So if I'm transmitting the information to you, I hope that you forward the information. So what I'm doing is to create a monitor mode in my interface, just watching if you are actually forwarding the information. So this you forwarding is like an acknowledgement for you for my transmission, knowing that you have actually forwarded this.
Thank you.
You're welcome.